Hi everybody, welcome back to Chem 121. It is Thursday night, and 1 week from today you will be finished with this class. Because we're almost done. What's coming up? Let's see, there's a quiz due tonight. Make sure to do quiz number 8 before the deadline. Quiz number 9 has been posted. I just unlocked it. I forgot to do that last night. I apologize. It is due on the day of the final. I would strongly advise that you do it before the final. You will have more important things to worry about on the final exam day, such as the final that I keep mentioning. Exam number 2 is on Monday, which is June 15th. Just like exam number 1, you'll have the entire day to do it. You get 2 attempts. You get the time allotment that I decide. I think it's 2 hours. I forget how much I give for this class, because it's different between my 2 classes. But whatever it was last time, that's how much time you'll get this time. And the content will be chapters 6 through 10. First one was 1 through 5, this one's 6 through 10. And then the final exam is everything, 1 through 10. So yeah, let's keep going. We were here last time. I gotta make sure my pen actually works today, because earlier this morning in the other lecture, my tablet died, and rebooting fixed it, thankfully, and it seems to be working fine now. At the end of the last lecture that we had last night, we talked about acids and bases. Very briefly, like, where are they, where in the world, like, what do they do, more or less, and, like, some structural things about them. We're going to define acids and bases formally in 2 different ways. The first one, right here, Lewis, we're not going to even touch this one, because that's more of a inorganic perspective. You don't need to know about that one. We're going to use primarily this one because it is the most complete. But we are going to talk about the Arrhenius method a little bit too. Those names might come up again. I'm not really sure if you will hear them again. Arrhenius is the simple definition of acids and bases that's not super useful for certain compounds. Brønsted-Lowry is much more complete and encompasses all different compounds that we can think of. So let's talk about Arrhenius first, because it's easier to understand, but it's not great. Arrhenius acids and Arrhenius bases require specific molecules to be present in order to call them acid or base. If you're an Arrhenius acid, you have H plus in you. So any substance that splits into pieces, that's what dissociates means. If one of those pieces is H plus, you're an Arrhenius acid. Okay. So that's the key one. For an Arrhenius base, the same rule, except one of the pieces that you split into is OH minus. So this is what a base would be. Acids make H plus, bases make OH minus. So we're going to use that as our sort of standard definition to figure out what exactly an acid is and what exactly a base is. However, the base definition isn't going to be complete. The acid definition is actually pretty good. Now, when I take any acid and I put it in water, such as HCl, this happens. So here's my HCl. It splits into 2 pieces, one of which is H+. Therefore, this is an acid. Now, H+ is hydrogen without an electron on it, which means that it's just a proton floating around on its own, so very alone. It's this little tiny charged proton, and it's very sad. Now, because it's very tiny and it has a very strong charge to it, anything with a negative polarity or charge or whatever is going to be attracted to this. It's going to find it. And if you drop HCl into a solution of water, water is by far the most abundant molecule around. So what happens is, each time you have HCl, the H and the Cl split apart, and the H plus ends up going to a water. Because there's water all over the place, and one of the waters will be like, oh, I'll take this H plus. What it becomes is this. This is called hydronium. Hydronium is more or less just how acids exist in water. Now, in chemistry, some people use this notation and some people use this notation. Either one works, but this one is probably the most correct at describing what we observe in the solution. So H3O plus is probably the best way to rate this, but if I say H plus, what I mean is H3O plus. They're the same thing. So all acids make H plus. By the same notion, all bases that are Arrhenius make OH minus. So here's my OH minus right here. So potassium hydroxide, which splits into potassium and the hydroxide ion, must be a base because it has OH minus in it. Arrhenius bases are all going to be ionic because in order to get OH minus, I need to pair it with something that's positively charged. And that positively charged thing, will be pretty much any metal you can think of. Potassium, sodium, magnesium, calcium, etc. And they all have positive charges on them because they're all ions. Now, what happens when you take an acid and a base and you put them together? You make water. H plus and OH minus makes H2O. This is why water is considered neutral, because when you make water, the reaction that we have called this is a neutralization reaction. We have neutralized the acid and the base. And then water is the midpoint of that, which is pH neutral. Now, with the Arrhenius base definition, we have a problem. And the problem is that we have ammonia here. Ammonia, if you put litmus paper in it, it turns blue. So that means that ammonia must act like a base. But where's the OH minus in ammonia? And the answer is, here's what ammonia does. When you put ammonia in water, what it tries to do is it will take an H plus off of water. And when it does that, you get NH3 plus H plus is NH4 plus. And then H2O plus, or H2O minus this H plus, is this. And so this is the hydroxide that is made and reacts with the litmus paper. But the addition of ammonia is what causes that to happen. So therefore, ammonia must also be a base. And it turns out a lot of different bases do this. They will react with water, take an H+, and they'll hold on to it, leaving the water as hydroxide. So just saying I have a OH minus in my structure isn't really good enough. So we have to come up with a new definition of this. And that definition is the Brønsted-Lowry definition. The definition for acids is pretty much the same, but the definition for bases is much better. Something is an acid if it donates H+, specifically a Brønsted-Lowry acid. And something is a Brønsted-Lowry base if it removes H+ from the solution. In other words, it takes H+ and keeps it for itself. So acids add H+ to the solution, and bases get rid of it. This is a much better definition because this helps accommodate ammonia. Ammonia removes H+ from the solution. In the form of water, it took away the H+ from the water. But the definition at least is true in this statement. So that's how we define acids and bases. Something that adds H+ to the solution will be an acid. Something that gets rid of it from the solution, either by getting rid of excess H+ that's already there, or taking it off of water to make hydroxide. Both of those are allowed by a base. Here's some examples of what acids and bases look like when they are undergoing reactions. In all of these cases, we're going to either react acids with water or acids with other bases. So today, what we're going to do is we're going to show these reactions just with water at first, and then we're going to start putting them together with each other to see how they neutralize. In this top reaction up here with my HCl, this H is added to this water to make H3O+. And in this case over here, oops, you know what I should do. In this case right here, the blue line represents where the H is going for onto the substance that is our base. So now what we're going to do is we're just going to put a reaction down and we're going to identify what acts like what role, because we just defined acids and bases as either adding H plus to the solution or removing it. In fact, we could go back to this slide right here and we could say in this first reaction up at the top here, HCl is an acid because it is putting H plus into the solution. But we could also say that H2O is removing that H plus from the solution. In other words, if this is acting like an acid, H2O is acting like a base. Down here, in the second reaction down here, ammonia is removing H plus from the solution, so it's definitely a base. But who is putting it in the solution in the first place? That's water right here. So here, water is acting like an acid. Because again, acids give H plus, and bases take H plus. In other words, you can look at these little arrows that I've drawn and follow the H plus. Where did it come from? That's the acid. Where is it going? That's the base. So the tip of the arrow on each of these is going to be my base, and the tail of the arrow is going to be the acid. So if you can do that for each process, then you're in great shape. You'll identify the right acid and the right base every time. So let's do that. Let's do that with some examples here. In this reaction on the left, who's the acid and who's the base? Identify which is which, and then type it in the chat panel once you got it. And then we'll draw arrows to show where the H plus is moving to and from. H2O is the base. Which one's the acid? I know that sounds like a well duh question, but it's a concept check. I want to make sure that everybody knows. HBr is the acid. There you go. So this H will move over here, which means that this is the acid and this is the base. All right, how about this one? I know we've already done that reaction because I keep going ahead of myself here, but that's okay. Which reactant is the acid, and which reactant is the base for this reaction? NH3 is the base, good. Which one's the acid? It's got to be H2O because I'm giving this H plus to NH3 so that I make NH4 and OH minus. So this was my acid, and this is my base. Good, you guys got it. Now what I want you to do Since this is a double reaction, it goes forward and backwards. It's reversible. I want you to tell me which is the acid and which is the base for the reverse reaction. Ooh. Look at me being sneaky with this double arrow here. H4 is an acid. Good. And hydroxide is a base. Excellent. Very good. Oops, I have the wrong pen, though. That's... There you go. All right. I mean, I guess that's a better way to look at it. So my text is just going to cover it up, but there you go. All right, so now what we're going to do is we're going to look at how these substances interact with each other across that double arrow, kind of like what we just did. In fact, if I go back to this previous slide right here... Oops, I didn't mean to actually hit the tablet there. If I circle this thing right here, and then I compare it to what it becomes after the H plus has been added to it, because I gave it H plus. These two things differ by just H plus. One of them acts as a base, and one of them acts as an acid. What these are called conjugates. And we link them together to call them a conjugate pair, because they differ by H plus. For any acid-base reaction, you will always have two conjugate pairs. Let me get a more distinct color. How about this one? So water right here, its conjugate would be hydroxide, because these differ by H plus. Really, I should be saying plus or minus H plus here. And so these, for water, are also... I could click on it. Where the heck did my cursor go? There it is. These are also a conjugate pair. So our task is going to be, first, identify all the acids and bases. And then we have to link all the conjugate pairs together. So let's do that. And that's the exact same reaction that we just did. That's the same reaction we just did. There we go. There's a new one. All right. So what I want you to do, starting with the reactants on the left, identify the acid and the base. Then go to the reverse reaction and use the products on the right to determine which one of them is an acid and a base. And then finally, link the conjugates together. Type it in the chat when you got it. We'll go over the answer in just a second. All right. Let's go over the answers here. I've got to get a better color than orange because I can barely see it. All right, so who is giving the H plus to who? Well, the H plus is going from H3PO4 to water. So this is my acid. This is my base. And then over here on the right side, this one is the entity passing the H plus to the other. So H3O plus will give up its H plus to H2P4O minus. And that means that it is an acid. Therefore, this is a base. And then finally, I got to link the conjugates together. So the conjugate of phosphoric acid is whatever differs by H plus, and that's this guy. And then the conjugate of water is whatever differs by H plus, and that's this guy. So the conjugate pairs always differ by H plus. What is the entity before and after you have added the H plus to it or removed it? For instance, phosphoric acid is H3PO4. When you get rid of an H plus, because it's acting like an acid, it will become H2PO4 minus. Water, when you give it an H plus, will become H3O plus. All right, let's do another one here. Sorry, that's just my answer, which is what I drew. Here's a different one. Identify the acids, bases, and then link the conjugate pairs together. All right, let's see how you did. In this reaction here, who is giving the H plus to who? Well, we know water will eventually turn into hydroxide, so it must be giving up the H plus, which means that it is the acid, and this is the base. Over here, in order to get this hydroxide to go back to water here, we would have to pass the H plus in this direction, so this is the acid, and this is the base. And now we can link the conjugates together. So who's the conjugate of water? Well, it's what differs by just an H+. It's hydroxide. And then who's the conjugate of bicarbonate? It's carbonic acid. There you go. All right, here's 2 more. Go ahead and try these. We'll go over the answers in about 5 minutes. I gotta go fill my water now that the water is turned back on here. All right, I see some answers for the first one. How about the second one? All right. Let's go over the answers here. All right, for this first one here, in this case, so I have HSO4 minus and H2O makes SO42 minus and H3O plus. So my H plus has to go in this direction, meaning that this is the acid and that this is the base. Over here, this guy doesn't even have H plus, so he can't be the acid. It's got to come over this way. That means that this is the acid and this is the base. And then if I want to link these together, who's the conjugate? This guy's the conjugate. And then the conjugate of water is hydronium. All right, that's the first one. All right, over here, I got water with this thing, whatever it is. This is actually called pyridine, but you don't need to know that. Those react to become pyridinium and hydroxide. So if water turns into hydroxide after it acts as something, then that means it must have acted as an acid in this case. And that pyridine is the base. Then over here, we got to turn our hydroxide back in the water, so it's going to need an H+, meaning that it's a base. It must get it from pyridinium, which is the acid. And then we can link our conjugates together. Here is a conjugate, and here is a conjugate. There you go. Hopefully you did good. All right, so that's your objective, is to identify the acid and the base in a reaction, and then link the conjugate pairs together. Oh, and there's the homework practice. So 1 through 28. All right. Now, something that you probably noticed is that water was doing something weird. Water was an acid or a base, depending on the situation, but it was never both at the same time. It was always one or the other. Any substance that can do this is called amphiprotic. An amphiprotic substance can either be an acid or a base, depending on what is around it. For instance, in this circumstance here, I'm passing my H plus over to water, so this is my acid, and water is a base. But in this circumstance here, now water is actually giving the H plus away, so it's the acid, and ammonia is the base. And you'll notice that oops, that was a really bad circle. And you'll notice that even though it's water in both cases, it's acting like a different thing. So water would be amphiprotic. Amphiprotic substances can go in both directions. It depends on what you are reacting it with. Water is by far the most common amphiprotic substance. Technically anything could be amphiprotic, but well, anything with an H plus, I guess you could say. All right. And then finally, some of the acids that we're going to be working with will have multiple H pluses. Here are some different examples of acids that have 1, 2, and 3 H pluses. HCl, HNO3, HBr, these are all monoprotic acids. They only have 1 H on them. Carbonic acid, sulfuric acid, those have 2, and then phosphoric acid has 3. Every time you remove an H plus, you have to take away the H plus from the formula where it came from. So H3PO4 would become H2PO4 minus to balance out the plus that I took away. And then if I did this again, I get another H plus and HPO4 2 minus. And if I did it again, I get PO4 3 minus. Whenever you do this sort of acid-base reaction where you toss off H pluses with triprotic acids or diprotic acids or whatever, you have to do it stepwise. So acids do not lose H plus all at once. They lose them in a stepwise fashion. And so that's shown on this next page here. I think that does it for that section. Yep. All right. Give me just a second to check something real quick. Okay, perfect. In the next section, what we're going to do is we're going to talk about how strong acids are and how strong bases are, and if we can draw any patterns. It turns out that there are some acids that are so strong that they dissociate completely. So their K value, if we were going to calculate it, would be infinite. And then for all other acids, their K value is small, so we have mostly reactants. Bases have the same thing going on. So let's look at these in a little more detail. Some acids completely split up, and these are strong acids. Now, I hate how the textbook does this. Every single other textbook in the world would not write this stupid arrow like this. They would write a forward arrow only. But your textbook is Garbo in some cases, so this is the arrow they use, whatever. For a strong acid, the dissociation is complete, so all of this will split up to form these two things. And so there shouldn't be any reverse reaction anyway, really. So strong acids dissociate completely. Weak acids do not. There are only 7 strong acids, and they are these: HCl, HBr, HI high, nitric acid, chloric acid, perchloric acid, and sulfuric acid. Specifically for sulfuric acid, it's the first dissociation only. If you are not one of these 7 acids, you are a weak acid. Weak acids don't dissociate much. And this is the arrow that the textbook uses, and this is at least a little more correct. Because both reactions do happen, the forward and the reverse. And because we only see a small amount of products in here, most of this stays here. So your textbook uses a big reverse arrow to say, oh, everything goes in this direction, but very little of it goes that way. And this is a little bit better. The common way to represent this is to just show a double arrow. So that's for strong acids and strong or weak acids. Strong bases and weak bases are all very similar in that anything that has hydroxide in it is a strong base and everything else is a weak base. And so here are some salts that you can make with hydroxide. The only reason that not every salt with hydroxide is in here is that some of them are insoluble. And if they're insoluble, you can't get OH minus in solution. You just keep the solid on the ground. Or at the bottom of the container, I would say. Normally, I would make you memorize the strong acids in Chem 121 in the classroom version. Strong bases are not worth memorizing. You just remember, oh, if it has OH minus in it, it's strong. As long as it's soluble. Generally speaking, anything with ammonia, anything with nitrogen in it that's acting as a base is going to be a weak base. So if I was going to draw the equilibrium for this reaction, which we've seen 79,000 times already today, you would draw a small forward arrow and a big reverse arrow because NH3 is a weak base, and it would look like this. All right. If you're looking at conjugates, there is a link between 2 conjugates. The conjugate of a weak acid will also be weak. So weak acids and weak bases will conjugate together. But the conjugate of a strong acid or base will be neutral. And so whenever you are pairing 2 things together to try and pair conjugates together, even though it's neutral, we'll still call it whatever you think it is as it's acting in a reaction. So like if I had HBr plus water, well, let me write that reaction out. So if I had this reaction, well, the HBr would pass its H plus over to the water, meaning that it's our acid and this is our base. And so you'd get this. we would still say that this would then act as a base, even though it's actually neutral. And this is our acid. Because in order to do this, to get the reverse reaction, that's what's got to happen. And then when we look at conjugates, so the conjugate of a strong acid is neutral. All right, there's the homework practice for this section. We are going to take a break after this slide here. And when we come back from the break, let me put the timer on the screen real quick. Boop. Doop, doop. Oh, there isn't a timer. I gotta fix that again. All right, we'll start the clock. Start the music, maestro. And I'll see you in 10 minutes. Oh, so close. So close. That's okay. Boop, boop. All right, so taking everything that we have covered so far, what we are going to do is we are going to put it together and stretch and yawn. That's exactly what we're going to do. We're going to yawn and stretch. Excuse me. And then we're going to predict products of reactions. That's what we're actually going to do. So in this section, we're going to define what a salt is. And then we're going to show how acids and bases react with each other to form water and salt. So a salt is any ionic compound that forms from an acid-base reaction, and the most common one that you see is table salt, NaCl. The formation of table salt occurs when you take sodium hydroxide and hydrochloric acid, like this. And the way that we do the reaction... Oh, where'd my pen go? There it is. The way that we do this is we first find water. So here's H+, and here's OH-, so there's my water. Everything else is the salt. So this and this would pair together as Na+, Cl-, which is just that. So the products of any acid-base neutralization reaction are a water and a salt if the base has hydroxide. And that's really critical. So you can't do this with ammonia. You will not get water. You will get a salt, but you won't get water. However, if you have hydroxide as your base, one of the products will always be water. So hydroxide is necessary. So all the acid-base neutralizations that we're going to do are going to be hydroxide-containing bases. And again, this is called an acid-base neutralization. So let's do a few more of these and try and predict the products. So the first thing that we're going to try and do is we're going to try and predict what the products are for sulfuric acid and potassium hydroxide when they are neutralized. So let's go over to this screen. That's not anything that I wanted there. There we go. All right. So I'm going to react these two things together, which means that they're going to go on the left side of the equation. All right. I'm going to put blank here because we might have to balance the equation to make this work out. But when we do this reaction, it is a hydroxide-containing salt, so we're going to make water. So water is one of the products. How much water will we make? Will we make one water? Will we make two water? It's hard to say until we break apart all the pieces. So first and foremost, let's split our acid into pieces. So we're going to make a sulfate and two H pluses out of this, because the H pluses can pop off one at a time. I'm just collecting all the pieces here. And then over here for my potassium hydroxide, I get the potassium part and the hydroxide part. Now, here's my water that I made. I'm going to cancel out my water as I make it. But you'll notice that I have left over H+. So what I need to do is I need more hydroxide to pair it with. If I had a hydroxide here, I could then react it with this H plus that's here. How do I do that? Well, I just go grab another one by putting a 2 here. So I get an additional K plus and an additional hydroxide. Which means that I can then do this. And now I've reacted all of my H plus with OH minus, so the reaction will be balanced when I'm done. I made 2 water, so I'll put a 2 up here. And then once you are at this point, everything that is left is the salt. Okay? So that's how we do an acid-base neutralization. You're going to try and find all the water and neutralize all of it, because it's a neutralization reaction. We got to neutralize all the things, right? Can't have a leftover H+, can't have a leftover OH-. So that may require you to add in extra pieces of one component or the other, just like when we were balancing the equation. And once I've neutralized all the acid and base, everything that's left over is the salt. You just throw it up there on the line. All right, let's do another one. Actually, I guess let's have you try this one first. There's more of them here. We're going to do a bunch of these. So let's have you do this one first. I'll give you a few minutes to do it. Write the balanced equation in the chat when you're done. Like how many water you make and what the salt is. Because I forgot to use the restroom during the last break. And so I'm going to go do that now. All right, how are we doing on this problem? I don't know what I'm doing. I'm hiccuping, apparently. Gotta drink more water. Do you have the answer? Type it in the chat. Type in what the products are. Oh, it's close. Your answer is very close. But there's a lot of 2s in there. Are all the 2s necessary? Well, let's find out. So if I'm going to split this into pieces, I got to write the equation here. Oh no, don't forget how to balance equations. I'm literally testing you on that on Monday. That would be very bad. All right, so let's split this into pieces. And I realize we're kind of doing this process is a little bit backwards for balancing equations, but it's the same sort of thing. We're taking inventory and then constructing our pieces from there. So first we got to find water, and here it is. We found water, so we made an H2O. We've neutralized everything at this point, so this must be the salt. There you go. So it's good that you reduce the KBr thing down to KBr, because it should just be KBr. Whenever you have a common number in ionic compounds, remember, we divide them all out, because these are just ratios of elements. But this is how you do it. So step 1, break out all the pieces. Step 2, neutralize all the water. Step 3, everything else is a salt. So let's give you this second one to do. Oops, I didn't hit the button in the right spot. Let's have you do this one. So do the same thing. Step 1, split up all the pieces. In fact, I'll even write out the steps on here to help you guys. Oops. So we'll just do this. Where is my cursor? There it is. Okay. I swear I'm getting old. Can't see anything. So step 1, break up all the ions. Step 2, neutralize all the water. Or I should say all the H+ and OH-. And then step 3, everything else is a salt. Sorry, my handwriting is really sloppy today for some reason. All right, so using that guideline, tell me what the products are for the second neutralization reaction. I'll give you a second to do that too. All right, let's go over the answers since I see some of these popping in here. So, oh, I ran out of space. Hold on. That's good enough. Boop. All right, so, oh, come on. All right, so step one, split up all the ions. So we got H plus, SO4, 2 minus, Rb plus, OH minus. Step two, neutralize all the water. Here's the water. Hooray! It's neutralized. We'll just put it up there. But I still have acid left over, so I need to do this to put additional base in the solution that I can then neutralize. Then step three, everything else is the salt. There you go. Everybody did it. Very good. Here is the last one. This is the hardest one. We give you calcium hydroxide and phosphoric acid. Neutralize the water and find me a salt. We'll go over the answer in just a second. All right, I see a bunch of answers here, so let's go over this one together, too. We'll just erase everything. All right, so we got H3PO4 plus calcium hydroxide makes blank and blank. So step 1, break up all the pieces. There are 3 H pluses and a phosphate. Step 2, there is calcium and then 2 hydroxide. So I can go 1, 2, but I have extra H left over. So I'm going to need an extra one of these things. Get another calcium here. And unfortunately, that only does this for my problem. So now I need to get another one of these guys to get another phosphate here. And more H pluses here. And even that doesn't seem to fix the problem. Ah! What do I do? And the answer is, well, I just get a third one of these. And this will work. And there you go. So this and this. So I made 1, 2, 3, 4, 5, 6 of them. 6 water. And everything else is the salt. So that's calcium 3, phosphate 2. And some students did realize that, hey, you should only ever have one salt, because everything left over is the salt, so I can only ever make one of them if I'm doing it this way. All right, there's your answers. And here is the homework practice. All right, the last thing we're going to talk about tonight is pH. So you may have heard of pH before. pH is a scale that is used to refer to how acidic something is or how basic something is. And I was going to have you guys do a lab on this, but I kind of ran out of time. And so that ended up getting shelved. We do have a pH lab for the in-person lab, and I don't really think it's that great, because you just sort of play around with paper and probes. And it's like, oh, cool, this makes a number. What does that mean? And that's really as far as we go. But let's talk a little bit about what pH means and how acids and bases relate to these numbers that are shown here. So the pH of a solution is a measure of how acidic or basic that solution is. And because it is a scale, that means we're going to have to calculate it. You're going to need your calculator one last time in Chem 121. The way that the pH scale works is it is a number on a scale from 0 to 14, with 7 as the midpoint. 7 is water. Something with a pH 7 is neutral. As the pH goes down below 7, those solutions are considered to be acidic. Those solutions will have H plus in them. So if you add more H plus, the pH goes down. Solutions that are higher than pH 7 will have less H plus or more OH minus. As you go further away from 7, the more and more acidic or basic you get. So pH 0 is extremely acidic and pH 14 is extremely basic. On the screen now is a chart that shows the pH of various things, although there is a typo on this chart, and I don't know how they didn't notice this. This should be a 1. You can't have 0 times something. And so what this chart tells you is the pH of things, and you can see as you get further away from the center, the more dangerous sounding the things become. So, like, going down from pure water to milk or urine or coffee, like, those aren't dangerous things. Those are things that we, with the exception of urine, those are things that we eat. Urine is something that is biological, though. You produce it and it comes out of you, so it's not harmful to your body. Because otherwise, when you made it, like, you would get seriously injured, and that'd be bad. But as you keep going down further, you'll notice that the things get more caustic and more aggressive, I guess you could say. So, like, tomato juice is very tart, but grapefruit juice is extremely tart. And then you get to stuff that just doesn't even taste good, like lemon juice and vinegar. Like, nobody drinks straight lemon juice or vinegar. If you do, you shouldn't do that. That's bad. And then finally, once you go down to the next step from that, you just go straight to stomach acid and then battery acid. So these substances at the extremes are very acidic. Just like these extremes up here are very basic. If you go up from pH 7, egg, seawater, baking soda, your blood is about pH 7.3. Toothpaste is like pH 10. And then we start getting into medicines that you take to get rid of acid. So like milk of magnesia is pH 10.5. Windex is like a pH 12 solution or so. Soapy water, depending on what soap you're using, can be very high pH as well. And then you get to the stuff where it's just dangerous. Like, don't get bleach or oven cleaner on your hands, because you will dissolve your hands very quickly. And certainly don't, like, dip your hands in Drano. Drano is like concentrated sodium hydroxide. And that stuff will just destroy everything, which is kind of the point. Oh, the drain is plugged. What should I pour in there? How about something gentle? Yeah, no, that doesn't work. So these numbers in the center are going to be our guide for approximating how much stuff is in there. And the way that we calculate pH is not on this page. So we're going to go over these 5 things here. There are 6 of them. I can't count. I'm tired and hungry, I guess. So something has a pH of 3. 3 is less than 7. We're going to call it acidic. Something with a pH of 8.5, higher than 7. And so you can see where we're going here. Oh, pH 7. That's exactly neutral. And then these 2 down here, you should be able to identify using your knowledge of the Brønsted-Lowry definition of acids and bases, and also the Arrhenius one. Alright. Oops, I want to leave that on the screen really quickly here. I need to check something. Okay, yeah, cool. So what is the formula for calculating pH? The formula is this thing. And this is something that chemistry students in 121 always try and figure out on their calculator. What the heck? How do I enter this? And so, fortunately, I have a calculator handy for you guys. If I could find it. Why is it not here? There we go. So all right. So you should be able to see my calculator now. And what this formula is when I calculate the amount of acid in my solution, I'm going to get a molarity. And so the molarity is what goes in here. So this is the molarity of H3O+ in the solution. And so what I do is I put in that number, And then I take the log of that number, and then I flip its sign. So let's suppose that I had this concentration of an acid. If I wanted to find the pH of that, what I would do is I would go to my calculator and I'd type in 0.150, and then I would log it. Where is log on my calculator? There it is, right there. So you want log. You don't want ln. Those are different. So you'd hit log, boop, and it'll just spit out a number. And then you need to flip the sign of what this is. So I go, boop, there you go. So the pH would be 0.82. So a solution that isn't that acidic, 0.150 is not like a huge number, right? Is still almost pH 0. It's about pH 1. It's very, very low on the pH scale. So this scale goes down very quickly. Let's suppose that instead I wanted to find the pH of a solution that was pH, I don't know, something very small. So like 0.000450. What would the pH of this solution be? Well, let's clear everything. So boop. And then we're going to type in 0.0000450. We'll hit log. Boop. And I'm going to flip the sign. Boop. And there you go. So this solution would be pH 4.35. How do you do sig figs with pH and logs and stuff like that? The answer is you don't. Just write 2 decimal places. Don't worry about sig figs. There are rules for it, but I'm not going to make you learn the rules for sig figs with logs on the last math thing on the last day of lecture. Because who the fuck cares? If you can punch these in the calculator and get the right result, that last digit, nobody's going to give a shit about it. That's fine. Alright, so that's how we use the formula to calculate pH. Now here's a question for you. What if I gave you the pH and I wanted you to tell me how much acid is in there? How do you go backwards? Anybody know the function that's the opposite or inverse of log? Like if I said my solution is pH 8.32. How much acid's in there? How would you find that out? Oh, you can't even see my number. There you go. How do you undo log? I'll give you a hint. We taught you this in Math 86, which is a long time ago, I realize. I'll give you another hint. That 10 there is not for show. I haven't mentioned it yet for that reason. And it's not tan. Tan is geometry. Log first, then the M. Now, that depends on your calculator. On my calculator, I type in the number, and then I push the button that says log, because it's going to log what's on the screen. Now, if you're using a handheld calculator, then, and the calculator makes you type in a command and then hit enter and process it, then you're going to type the log button first and then the number, and you might need to put parentheses. The other thing you can do is remember Wolfram Alpha? I don't remember if we used Wolfram Alpha much in this class, but we certainly used it at the start. Let's see here. Window capture 2 is Wolfram Alpha. There we go. So we can use Wolfram Alpha here. Oops, hold on. Let me do this. And so if you want to just type in the equation here, you could say minus log of whatever number you were doing. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Oh, it thinks that I'm using log E, so you want to do log 10. There you go. And that'll give you the right number. So you can use Wolfram Alpha to do this too. Just be careful that you're telling it to do log 10 and not just regular log, because what it thinks log is actually this. There's a bunch of different logarithm functions out there, and you want the one that is base 10. That'll give you the right answer. That's why I said make sure you're pushing on your calculator. You want to hit the one that says log and not the one that says natural log. So now we got that, so let's close this guy again. How do I undo this? So it's not tan, unfortunately. It's not sine or cosine, because those are all geometry crazy weird things. I'll give you a hint. It doesn't look like the word log. It is on my calculator, though. You can actually see it here. It is one of these buttons. What is the symbol after parentheses? This arrow? That, I think, is a backspace. I can't actually use it. So ln is not natural log. Or, I'm sorry, it's not the inverse. So I'm going to hit clear everything. And what we're going to do is we're going to try and find things. So if I log 5, boop, and I push another button, that's the inverse, I should get 5 again. So let's see. Boop. Nope. Boop. Boop. Oh. Well, that didn't work, so nope. Boop. Boop. Ooh! Look what happened there. What's going on here? Inverse is actually to the -1, so it's not. But notice how that when I log something and then I take 10 to the power of that number, I get my number back. I can do this with any number I want to. So if I log 9 and then take 10 to this number, I get 9 back. So the inverse of... Oops, I can't move it there. That's not going to help me. I don't really know where to put this right now. So let's erase this. So in order to solve this equation for this number right here, what I have to do is I have to take both sides. I have to do this to it. First, I got to move this negative over. So I get minus pH equals log base 10 of the amount of hydronium there's in there. And you can't see it because my damn calculator's in the way, so hold on. And then what I have to do is I have to get rid of this function. And the way you do that is you do 10 to the power of that function. And then those things cancel out. But what I do to one side, I have to do the other. So 10 raised to the power of negative pH will then give me the amount of acid that's in there. And that will give you a molarity. So let's do what we just thought about. So if I want to find something that's pH 8, so like, say, some baking soda in water, how much H plus is in that solution? Then what we would do is we'll put the calculator back on the screen. We'll shove it up here or something. Let me clear everything here. And we're going to type in our pH, so 8.32. I'm going to turn it into a negative number. And then I'm going to do 10 to this number. Boop. And I got 4.78 lots of digits times 10 to the minus 9. So the concentration of H plus in a solution that is pH 8.3 is 4.79 times 10 to the minus 9 moles per liter. which is, holy crap, that's small, right? I don't know if you were expecting the number to be that small, but whoa, it's that small. So the reason that we have this log scale is because the range of H plus that you can be exposed to goes from like 10 to the 2 all the way down to 10 to the minus 15. And so if we had to just this huge range of numbers, there's really no way that we can comprehend that. So the way that mathematicians have decided to work with this is they use what's called this log scale. And when on a log scale, every time you go up by an order of magnitude, you go up by 1 on the log scale. So now we have a range of numbers that goes, instead of being from 10 to the 2 all the way up to 10 to the minus 15, it instead goes to like -1 to 15. So the log scale is more convenient because me saying, oh, it's pH 4 is easier to conceptualize than, oh, it has 1 times 10 to the minus 4 moles per liter of acid. So when you work with pHs that are low, you will get acid H plus concentrations that are still fairly small. But if you work with pHs that are high, you will get H plus concentrations that are extremely small. Okay? And we haven't even done OH yet, but we're going to do OH next week. So what are you responsible for on the exam? Everything up to this slide. This is the cutoff. So exam 2, the last thing in chapter 10 that I will ask you to do is calculate pH. So I might say, here is an acid. Its molarity is 0.00002. Tell me the pH and type it into Canvas. And that's what you'd have to do. I might also make you do what we just did right now, which is, hey, here's the pH. It's 7.5. How much acid is in there? Tell me its concentration. And so you'd have to do the reverse process that you showed me here. The next few slides will actually show you this in more detail, and then they'll start showing you how to solve for POH, which is the exact same thing but with hydroxide instead. No OH stuff like that will be on the exam. So I'm not going to make you calculate POH on exam 2. It might show up on the final, but it won't show up on exam 2. There's only like 20 slides left because I actually don't do the section on salts. I just skip it. So we have 20 slides left, and then the class is over. So I'm going to stop here so I don't overwhelm you with too much math before exam 2. I think learning how to log and how to unlog with the 10 to the power of button is more than enough math to get you guys probably angry. So I'm sorry for ruining your weekend with math. But please do make sure that you do some exercises for this. How did I type it into Wolfram Alpha? Sure. So let me find that window again. Oops, hold on. So that's this one. Oh, calculator, hold on. Let me do this, actually. That's the wrong button. Sorry, hold on. So if I do this, now I can make it bigger and you can see it. So if I wanted to do the pH of something, I would type minus log 10, parenthesis, and then whatever the molarity is. So, I don't know. I've clearly done this one several times. This is actually the pKa of vinegar, which is why that's in here. And then what it will do is it will tell you the answer right here. And you only need 2 decimal places. Now, if you wanted to go the other direction, then what you would do is you'd say 10 to the, and the power is that, minus, and then whatever your pH is. So if I wanted to figure out how much H plus was in a 11.31 pH solution, this would be the answer. 4.89 times 10 to the 12. Sorry, minus 12. 10 to the minus 12. And you can even just sit here and play around with it. So, like, in a pH 1.31 solution, this is how much H plus would be in there. Did you get all that? Is that all you needed for the Wolfram Alpha? So you can use either of these. I was using, this is Windows Calculator up here. Wolfram Alpha is just available everywhere. And obviously you're allowed to use this during the exam. You can use whatever source you want. I'm not going to stop you or restrict you or make you use the browser lockdown or whatever. I don't care about that. I just care that you're able to do it in some capacity. Hooray. Okay, cool. Then we're done here. Hooray. I want to thank everyone for coming out. I hope that you are able to study well this weekend. Exam number 2 is chapters 6 through 10. Make sure that if you have questions over the weekend, you send me an email when I'm not writing the exam, because that's immediately what I'm going to start doing tomorrow. I will be available to answer your questions. Make sure you ask them. Have a wonderful weekend, and remember, good luck. We're all counting on you.